Go. Question 5. A particle P of mass 0.4 is at rest on a horizontal surface. The coefficient of friction between P and the surface is 0.2. A force of magnitude 1.2 metres acting at an angle of theta above the horizontal is then applied to P. Find the acceleration of P in each of the following cases. So we've got 4 different versions of what theta can be, varying from 0 up to 90. So the first one has theta as being 0. That means the force of magnitude 1.2 is acting at the horizontal applied to P. So let's see how we can construct a little diagram to get a feel for what's going on with this. Here's my particle. Let's put in the things that are obvious to start with. We've got a weight of 0.4 g. We would have a normal contact force, which I'm going to call R. Now in this case, in part 1, we've got a horizontal force of 1.2 newtons. There it is. It's held in equilibrium though, is it? No. Hang on, what's going on? Find the acceleration. So we know it's a rough surface. So based on that, I think friction has to be here. There's my frictional force. So that's my diagram. I'm told that mu is 0.2. So let's work on what we can do with that diagram. If I resolve in a vertical direction, R is 0.4 g. We've got friction now. I don't know if it's moving or not yet, but let's think the maximum value that friction can take is mu times R. So that's 0.2 times 0.4 g. So that is 0.784 to 3 significant figures, newtons. So let's resolve in the horizontal direction now and see what the acceleration comes out as. 1.2 minus F, which is 0.784, is equal to the mass times the acceleration. And if I rearrange that equation, do that subtraction, divide by 0.4, I get A is 1.04 metres per second. And I think most of you did come up with that value for part 1. So part 2, we have a slight change in what's going on here. We have the particle on the plane. Let's put the same, we've got 0.4 g. There would be a normal contact force. This time we've got the 1.2 force at an angle of 20 degrees to the horizontal. It would still be wanting to move in this direction towards me, so friction would oppose the motion. So there is the frictional force. First thing to remember is that we've actually got another force in the vertical direction, the vertical component. So the reaction would be different. So we're not going to go straight in with the same value of F max here, because R is different. We've got that R plus 1.2 sine 20 is equal to 0.4 g. Okay, we've got a different value of R. Rearrange that and we come out with R as being 3.51 newtons this time. Okay, that's quite an important start point, isn't it? So, the maximum value that friction could take is mu R, so it's 0.2 times 3.51, which this time comes out as being 0.702 newtons. That's the maximum amount that friction could be. So if I resolve horizontally, I've got 1.2 cos 20, that's the horizontal component of that one. Take away F, let's take away F max, is 0.4 times mass times acceleration. And this one gives us A as being 1.06 metres per second. Okay. And it's interesting, isn't it? I mean, it's all quite interesting. It maybe feels like a slightly odd answer. That there, the force was along that way. In the first one, the force was horizontal, and the acceleration was 1.04. Here we've got a slightly greater acceleration. feels odd, because the horizontal component of the force is less. But it's because it's lifting up, it means the frictional force is reduced. So there we are. We're on to part 3. Now it gets really interesting. So part 3, the angle increases further. Here's our particle. We still have the weight acting downwards. We still would have a normal contact force, but it again would be a different contact force. We've got 1.2 at an angle of 70 degrees this time, and frictional force would still be opposing that. So, if we resolve in our vertical direction again, because we need to find the new value of r plus 1.2 sine 70 is 0.4 g. So this time r is 2.79 newtons. Okay. So F max is 0.2 times 2.79. So the maximum amount that friction could be in this case is 0.558 newtons. So that's a lot less. If we resolve horizontally, we've got 1.2 cos 70 minus 0.558 is mass times acceleration. And this time it comes out a little bit weird, because this time 1.2 cos 70 take away 0.558 is minus 0.148 and 0.4a. And we've got to think sensibly about what's going on with this, because what we can't do is just end up with a negative value of acceleration and say, yeah, that's great. Because logically, what would that mean? That would mean that it was going in that direction, and it was accelerating in that direction because the frictional force is pulling it in that direction. That's more than the force coming in that direction. And that's nonsense, isn't it? This was the maximum value that friction could take. It's if the force isn't sufficient, if the force doesn't match up to this value, friction would take the force that is equal to the force pulling in the other direction. It can't be accelerating due to friction, as A can't be negative. Friction is not limiting in this case, therefore A equals 0. We have to conclude that because the friction can't be producing the acceleration, friction didn't take this maximum value, it was less than that, and we ended up with A being 0. We must conclude that A equals 0 at the end of this. So what happens with the last one? Part 4. This time we have the force at 90 degrees. Okay. So here's our particle, 0.4 g. Now if the force is at 90 degrees, then we've got that situation. And let's think logically about what's going on with this. There's no way we could have any horizontal motion. There's no horizontal component of anything going on there. So there's no horizontal acceleration. But the question didn't say find the horizontal acceleration. It said find the acceleration of p. So the only way that p could have any acceleration is if the 1.2 force is enough to lift it off the table. Okay? If it was enough to lift it off the table, r would be 0 because it was lifting off the table. In fact, if it was enough to lift it on the table, we need to check, is 1.2 greater than 0.4 g? And it's not, is it? Because g is 9.8, and so 0.4 times 9.8 is going to be much greater than 1.2, 0.4g is greater than 1.2. The weight is greater than the force trying to lift it off, therefore it remains on the table. There's no horizontal force. And the question said find the value of A. We conclude A equals 0. Okay. It's quite important that we do a calculation here not involving R, because of course what we're interested in is if the particle is being lifted off the table, and if it is, then R would be 0. So we don't want to include R in our calculation if we think about that. Okay? There we go. Quite a lot going on, wasn't there, for 11 marks, but quite a lot of marks for it as well. There we go. And that's